7 deadlocks. And it's really not a complicated topic. A system consists of resources, right? What are resources, for example? You think of a resource in a system? RAM, memory, we could call it, let's say the CPU, the hard drive, the printer, those are resources. We can talk about resources in an abstract way and call them R, R1, R2, Rm. It could be like we were CPU cycles, memory, IO devices. Each resource type R sub I could also have a number of instances. They could be like 3 printers. You have 3 printers connected to your computer. And then 3 different processes could print at the same time. Each process utilizes a resource as follows. First, it requests the resource. The operating system then has to handle that request. Then it uses it, and then it releases it, presumably, at some point. We're going to assume that it does release it. So what is a deadlock? A deadlock is when 2 processes are waiting for each other. What does it mean they're waiting for each other? Well, if I am using let's say I'm a process and I need the printer and the memory, and you're a process and you need the same memory space, let's say, or well, memory is a bad example, but let's say a printer, I need the printer and the hard drive. There's only one printer and one hard drive, but I need them both. And you're a process and you need the printer and the hard drive. So let's say I asked for the printer and the operating system gave it to you. And you asked for the hard drive, the operating system gave it to you. Now I am waiting I can't continue until I get the hard drive. And you can't continue until you get the printer. So I'm waiting for you to finish with the hard drive, and you're waiting for me to finish with the printer, but we're never going to finish because we're waiting for the other one, because we're not going to go on until we have both resources in hand at the same time. So that's called a deadlock. I'm waiting for you and you're waiting for me. I'm waiting for a resource that has been allocated to you, and you're waiting for resources that have been allocated to me, and it's a circular situation. I'm waiting for you and you're waiting for me. There's never a way to get out of that. That's called a deadlock. So the characteristics of a deadlock are that there is mutual exclusion. Only one process at a time can use the resource, right? If we could all print at the same time, then they wouldn't have this problem. I wouldn't have to wait for you to finish with the printer. I could get it while you get it. Of course, you can't print at the same time. It's a great example of something that inherently cannot be shared, because if we would be printing at the same time, then my letter and your letter would be intertwined and it would come out like garbage, come out gibberish. So that wouldn't work. Hold and wait is another characteristic of deadlock. If you don't have hold and wait, then you want a deadlock. And in my case that I gave you, where I'm holding the printer and waiting for the hard drive, then I'm holding and waiting. If we wouldn't allow that, if the minute somebody asked for something and he couldn't get it right away, he immediately dropped everything that he had, then we would never have deadlocks. And if any one of these conditions is not met, we won't have deadlock. The third condition is no preemption, which means that the operating system doesn't come along and say, oh, I'm going to take away the printer from you because somebody else wants it. So if that would happen, then that would also solve the problem. And the other thing is there has to be a circular wait. If I'm waiting for you and you're waiting for George and George is waiting for Harry, then there's not, even though we're all waiting, eventually Harry will finish and then George will get it and then you'll get it and then I'll get it. So that's not circular. It's only a deadlock when it's circular, when I'm waiting for you and you're waiting for George and George waiting for me. So then we have a circle, and then and that'll never end. So if we can avoid any one of these conditions, we will not have deadlocks. Now, what characterizes a system that isn't deadlock? Well, what characterizes it is that the processes are not doing anything. You have a process, and it's like you're waiting for it to open your email, and it's just never opening it. Or you're waiting for something to happen. You're waiting for a program to go to the next step in the program, and it's not getting it. So what would the other solution be? We could always go in and kill the process and start it again. That's called human preemption, right? The human being comes and preempts. Or we could turn off the computer. That would also be human preemption. That's actually a solution. You could say deadlocks are very rare, and whenever they happen, I'll just rely on the user to turn off the computer. And that's a nice solution for your own personal PC, but it's not a very good solution for a server that's serving thousands of people simultaneously.
But
You don't want to turn it off and then all the people get disconnected.
that would require you to restart the whole process.
Right, but the deadlock won't always happen. It only happens because of a certain timing event. That I happened at the same moment as you wanted that. If I got both the printer and the disk drive, then it wouldn't be a deadlock. I would do my job and then you would get them.
Yeah.
You see what I'm saying?
Yeah, just gotta hope that it's not a super long process.
Well, we're assuming the process is, well, even
I
if
mean,
a
like,
process is
it's a
super
program that
long.
does like 1,500.
Okay, that's an
things.
important point. Even if a process is super long, if it eventually finishes, that's not called a deadlock.
I mean, let's say it has like 1,500 times that it goes to CPU or something else, and
Oh, and then keeps doing
it'll
it.
take an hour.
It
so
could be
you
that
know-
it could be that that solution won't work because it just keeps happening. Yeah, it's possible. Okay, so we're gonna resource allocation graph. We're gonna make graphs to try to and analyze systems. A set of vertices V and a set of edges E. V is partitioned into two types. In other words, what are these vertices? Well, the vertices are the processes. And then there's the resources. Those two types of vertices really, I don't like that. Let's go straight to the picture. Look, a process is, let's say, like this, a circle. And a resource is, let's say, a square with little squares inside it. What are the little squares inside it? It means they're instances of that resource. So for example, the square could be hard drives, and inside could mean that I have 4 hard drives, which means anybody who wants a hard drive, I can give him one of these 4, and I can handle up to 4 requests simultaneously. If we're talking about a request, then P requests the resource, that's an arrow pointing from P to the resource. There if P is holding the resource, then it's an arrow from the resource to P, means he's got it. And usually it's if there are individual resources, if it's not just one resource, then we'll draw the line to the center box, to the center of the particular, to one of the particular resources, like in this picture. Right, so we define this arrow. When is a request edge, when P is pointing to the resource, it indicates that P needs or requests the resource. And an assignment is in the other direction, when the resource is pointing to the process. That's what we saw already. Okay, so here you have an example of a resource allocation graph where you see these nice little P's, and the question is, of course, is there a deadlock here?
No,
When would there be a deadlock?
then P3 is waiting for.
Well, you have to have circularity, right? Do we have circularity?
No, we don't, but P3 is.
Right,
doing
because
something.
actually, in these kind of graphs, the circularity is actually visibly discernible because the arrows would have to be pointing in the same directions. If this arrow would point in the other direction, then it would be a circle.
But
So
they're not using the same instance of the resource.
That's fine, that's not that.
Would that be still because?
Well, the truth is, if this arrow would be pointing in the other direction, it would be illogical because there's an available resource. Why would he be
Yeah.
requesting it and not getting it? If it would be pointing in the other direction, that means he's requesting it. So it would have to be only one dot here, right? The dot indicate, the arrow will remain like, for example, here, what does this mean? What does it mean that P is pointing to resource 3?
It's waiting.
He's waiting, he's requesting P. He's waiting for P3 to finish. Eventually, sometime in the future, P3 will finish, and then P2 will get this resource, and then the arrow will reverse direction, and then P2 will have everything he needs. He'll have an R, he'll have an R2, R3, R1, and R2. And then P2 will finish. And once P2 finishes, then there's nothing to stop P1 from finishing. So that's, if you make a graph like this, why do we make a graph like this? I mean, visually, it's nice and well to look at it, but we actually could program it. We actually could program like a table of vectors, and we could keep track of what everybody's pointing to, and then we could go through that table and look for what? Look for circularity. Look for something, but that would require a lot of checks. It's like more than n, it's either n Bua or even more, n squared. But it would require, you could make a table of all the resources and all the arrows that are connecting it, and there's could be an algorithm for that. So we draw it, but really what we mean is we're gonna program it. Now what about this position? Is this a deadlock? I added another line.
Now it's circular.
Yeah, looks like there's a circle.
There is a circle.
No, there's not.
Something bad is probably happening. There's a circle.
Because What? Now we don't know. Before we said it's not a problem because eventually P3 will finish. Now P3 will maybe never finish because he's waiting for P1 and P1 is waiting for P2 and P2 is waiting for P3.
Would we say
So everybody's
that-
waiting for everybody and it'll never finish, perhaps. It'll never finish.
Would we say that there
It'll
are
perhaps, definitely.
does it make sense to say like linguistically that there are two deadlocks here? Like, would we say that?
No, it's one deadlock. The deadlock, the players in it, if I'm waiting for you and you're waiting for Fred, and Fred is waiting for me, that's one deadlock. The players in that deadlock are three.
Right, but you could also say that P3 is just waiting for P2 and then.
Oh, you're saying like this,
Right.
P.
Right, there's like one small.
You're
deadlock
saying
that's
this
larger.
one, this is also a circle here,
Right.
between 2 and 3
No, but
is a circle,
it
but
is-
there isn't a circle between 1 and,
No.
right.
I think that's wrong because the R2 has two instances, so the only reason it's a circle is because the second instance
Right.
of R2 is taken.
I'll just call it the P3
You could-
deadlock.
I mean, it's immaterial, it's not, it's not a question we ask, we do not ask how many deadlocks.
Okay,
It's-
but we would say that in linguistically.
But it's a good question for an exam, but I won't ask that, I want, that's
I'm
not,
just,
again, it's not a thing that we would ask, we're not gonna
I'm just
ask,
calling it
is there, how many deadlocks are there? I might ask, what would it take for the deadlock to be broken, and you might say 2 things have happened. Okay. Here's a graph with a cycle, but no deadlock. Look at this. Why is this no deadlock? Look, we have a cycle. Look, it's a circle, the pointing. Visually, we would detect it if our algorithm just checked for circularity, we would say it's a deadlock, but it's not a deadlock. Why? Because eventually P4 will finish.
And then there'll be an extra.
And then there'll be an extra instance, and so we have to, right?
Yeah, but
and
we don't have all the squares inside, circles inside the square of the cycles.
Right. If we have only one cycle, if we only have one instance of each resource.
Yeah.
Then circularity would
Would be a deadlock.
always be a deadlock, right? Basic facts, if the graph contains no cycles with no deadlock, if the graph contains a cycle. If one instance per resource, then we can always have a deadlock. If there's several instances, there's possibility of deadlock, as we just said. Okay. Methods of handling deadlocks, we could try to ensure that the system will never enter a deadlock state. Or we could allow the system to go into a deadlock state and then identify it and by this graph and recover. Or we could ignore the problem and pretend the deadlock never occurred. And this is actually what Windows and
I guess
Linux
it does.
use, because we just hope it never happened. Because the point is like this, if the medicine is worse than the cure, don't take the medicine, right? If the amount of energy, the amount of programming we'd have to do to detect these errors or prevent them, it slows down our system more than the actual deadlock does, then it's not worth our time.
But wouldn't deadlock be terminal?
Deadlock is terminal, but it may happen very rarely. It may happen once in 100 years. So then
You can always have
it's
a-
not worth spending, it's not worth wasting our CPU all the time on something that happens once in 100 years. It's like, if there would only be one guy who made viruses in the whole world, and he only did it once every 5 or 6 years, then maybe we wouldn't be worth having virus checkers, because and if he was bad at it. I'm just saying, you always have to do something called, managing your resources against the risk. Yeah, the one guy who did this. Okay.
One guy answered that.
So how can we prevent deadlock? We can restrain the way requests can be made. For example, we could try to prevent mutual exclusion. We could have shareable files. If we have shareable resources like read-only files, then we won't have deadlocks. But there are sometimes things that are intrinsically mutually exclusive, like a printer. A printer, like I said, you don't want 2 people printing at the same time. Right? You get a confused printout.
Nowadays, don't think printers have like their own data within them with like queues and like anyone can talk to them.
Yeah, okay, yeah, right. You can put things on the queue. If you're just putting it on the, no, but let's say 2 people are trying to put it on the queue at the same time. There's always gonna be a bottleneck. If I'm trying to put on the queue at the same time as you are, you know what I mean? So it has to be, no, I gotta wait for me to finish putting onto the queue. You're right, by having, I'll explain to you, it's a very important point, which is that by the printer having its own memory and having its own and having its own, let's say, device driver, we can communicate with him and say, here, take this file, and if the printout of that file might take 5 hours, but we don't have to wait 5 hours
Yeah.
We'll just send him the file and he'll hold the file. And now the next guy can come and talk to him. So the amount of time that the first process is holding the printer is not equal to the time that the printer takes to print.
Yeah.
It's just the time it takes to send him the message. Okay,
Unless printer's memory is full and he has to wait for it to clear up.
yeah, like it's always, well, we try to avoid, so denying mutual exclusion is not a viable method to prevent deadlock. What about hold and wait? Must guarantee that whenever a process requests a resource, it does not hold any other resource. Well, that would, right, if we would say like this, you could only have one thing at a time. Then we would never have deadlocks. You could only have one thing at a time. Require the process to request and be allocated all its resources before it begins executing, all or nothing. So you can say like this, oh, not that you can't have only one, you can have as many as you want, but before you start running, tell us all the things you're gonna ever need, and either you get them now or don't get them. So if you don't get them all, then you won't even start. So you won't be part of the problem, you won't be part of any loop, because you're not even existing, and if you are existing, it must be that you got everything you need. So that's would be one thing, but that's also kind of crazy, because maybe the processor in the future will need to print, but he doesn't even know, so he can ask for a printer now, even though on the off chance that somebody wants to print. Allow a process to request resources only when the process has none. That's what I said, that should be only one. Both approaches have low resource utilization, because one process may hold many unused resources. Like I said, I have to ask for the printer, even though I'm not printing, and who knows, in the future I might print. And may cause starvation. Processes which needs many resources may never find them available and never start. If he needs a lot of stuff, he may never be able to get them all, because there's always somebody else got one of them.
What's the issue with the second method? That you can only hold one thing at a time.
Well, but also that would work, except that what if you need two things at the same time? You can't guarantee that all processes only need one thing. Okay. No preemption. So we could have preemptions. We could just say, let's preempt. So there's a couple ways, I wrote two here, two ways of implementing it. One, if a process is holding some resource, requests another resource that cannot be immediately allocated to it, then all the resources currently being held by him are released. And you restart only when all the resources are available. In other words, the minute you're waiting for something and you're holding resources, you terminate. You essentially terminate, because you can't, you drop everything, or you freeze. You could say you freeze, you drop everything, and then you wait until they're all available and then start up again and get them all. If a process requests a resource held by another process, if that other process is waiting for a resource, we preempt the desired process. This is very clever. We're saying like this: I am a process and I'm asking for something from you. Now, if you are waiting for anything, you're waiting for something. And it could be not a deadlock here. It could be that could be that I'm asking from Fred, and Fred is asking from Harry, and Harry is waiting for Martha. So, but I asked from Fred, and he's waiting for Harry. So I can take it now from Fred, because he's waiting. It's not a deadlock, but I'm going to prevent deadlocks, because if it would have been that instead of for Martha, he's waiting for me, I would have prevented the deadlock. But this way, it's a little bit overkill. But the point is, I'm only doing it, I'm not going to take it from you always. It's not like if I want it and you have it, I'll just take it. We'll say, I want it and you have it, and you're waiting for something that you haven't got yet. Then I'll take it from you. So we preempt the desired resource for the waiting process. Otherwise, we wait. We restart only when all resources are available. Okay. This is good for CPU allocation whose state can be stored, not good for printers. Right. In other words, think about that. If I would preempt the CPU, no problem. So we'll store all the data in the CPU into the memory, all the registers that are in that CPU. Right? He's got all this data. He's in the middle of a program. We'll take the CPU away from him, and we'll put all this data somewhere else. But if it was a printer, how could I preempt the printer? You're in the middle of printing, and now I'm going to preempt you. So now I'm going to print, and when I finish, I'll give you back the printer. But you were in the middle of one line, you printed one letter, and then you got stopped, and now how you get to restart the whole print job? You can't really. It's going to be complicated. You can't just pick up where you left off, because the page, the document will look messed up. You have to rip the pages in different ways. So it's not such a good solution for printers, for example. So. Circular weight, so wait, so we basically said that there is a solution with mutual exclusion to prevent that. There's a solution to prevent this, and there's a solution to prevent preemption. I mean, to allow preemption. And the fourth condition also, circular weight, impose a total ordering of all resource types and require that each process requests a resource in increasing order of enumeration. What does that mean? Well, I'll give an example. And this actually system, I don't know, for some reason I like this system the best because when you think back, it doesn't have any situation where it won't work. It may also limit resource utilization, but let's think about it. What we do is like this. We say the tape drive is value 1, and the disk drive is value 5, and the printer has the value 12. That's what we mean by we impose a total hierarchy on all the resources. There's a hierarchy. Some things have a higher place, have a higher number, some things have a lower number. Okay, if a process requiring a printer and a tape drive. Oh, a process requiring a printer and a tape drive must first request the tape drive and only then the printer. Why? Because the tape drive is 1 and the printer is 12. So you got to go in order. You can't request 12 and then request 1. It cannot occur that one process is holding a printer now and requesting a tape drive. So circularity is denied. In other words, the order is always directional, single directional. There's never circularity. Because if I want, let's say I have a disk drive. So I can ask for a printer, but I can't ask for a tape drive. So if I'm asking for this printer, that printer, the person who has that printer can't be waiting for a tape drive. The most he could be is waiting for what I've got. Oh, no, he can't. He can't even, if he's got a printer, he can't ask for anything. Once he's got to the end, he can't ask for anything. So you have to order, you have to ask in the right direction. To first ask this and then ask this. It's very similar to, did we talk about the philosophers? And remember we had a solution? What was our, well, my favorite solution over there was that that you first, if you're odd numbered, you take the left one first. And if you're right numbered, you take and if you're odd even numbered, you take the right one first. So it could never happen that there's circularity again. It's the same kind of idea. You give a structure to the way they request. The requests have to be in a certain order. In the philosophers, they have to be in a certain order, depending on your odd or evenness. Then you have to go either left, right, or right, then left. And here also there's a certain order. I have to go always up. And if I want to, I have to request in the right order. So there can never be circularity. This is a very simplistic example, but this is the one I got from, and it says like this. I think we saw this before, actually. We did, this is with threads, we have a thread, mutex lock, that's a function, should really have underscores here. And basically I'm waiting for the first mutex, and I need to go in, I need 2 mutexes. So I go wait for first mutex, wait for second mutex. Now, that seems like right, but the other program does it in the reverse order. He does get the second and then get the first. So it could happen that I get the first and then he gets the second, and now I'm waiting for the second, but he's got it. And he waits the first and I got it. So this would be a deadlock. Nothing to do really with resource. What's a resource? The mutex itself is a resource. I'm waiting for resource mutex lock a second, and he's waiting for me, for mutex lock 1. What about this example? This example looks great. This is an example for, let's say, I want to send money to a bank. I have 2 accounts. I have the account from where the money comes and the account to where the money goes. So first I lock where I'm taking the money from. In other words, the from account. I don't want 2 people. Let's say the guy's got $1,000. I don't want to have a possibility that he can twice send $1,000 to 2 different people. I want to lock the from place. So I lock the from place. I also want to lock the to place. Not so obvious to me why you want to lock the true place, but let's say I want to lock the to place also. I don't want to get the data screwed up. It could be that I'll read the data, what's there, and then I'll add 1,000 to it. It's like that 12,000, now I'll make it 13. If somebody else would get it, he would also read 12, and we both make it 13, but it really should be 14. Because I added 1,000 and somebody else added 1,000. So it should have gone from 12 to 14. But if we both read it before we wrote it, we read it as 12 and we changed it to 13, it'll get screwed up. So we need to lock the other side also. So we lock this from side and lock the to side. Then we, that's just defining what the locks are. This is just define that lock one is the from and lock two. And then we lock one, lock two, withdraw the money from, and the amount of 100, and we deposit the money to two and the same amount, and we release the lock and release the lock. That looks great, right? Wouldn't that be the way you would write it? That should be perfect.
I think that's perfect.
What? How could this be a problem? This is actually a problem.
What?
Why would this be a problem? If all the access to the bank accounts are in this order, it would seem we'll have no deadlocks, because we're always doing it in the same order. It's not like one is doing it the other, it's not like one is doing it to and the other is doing it from. They're both doing it from and to. So when could there be a deadlock?
I read the text.
Between lock
You read
one
the
and lock two,
Cheated.
What?
between lock one and lock two?
Not between lock one.
No,
No. The problem is that the to and from are relative things. What if just at the same moment I want to send money? I want to send money from my account. So my from is Nachum. And somebody else on the other side of the world is trying to send money to Nachum. So wait a second.
so if he requested.
And actually the same person. I lock myself, and then he locks himself. I lock myself, and I'm trying to send to that other person in the other world. So he's going to be my two, but he locked himself because he's about to send to me. So his from is himself, and my from is myself, but my two is him. So I can't, when I come to the two to try to lock him, he's already locked by him because he's about to send money to me. And it doesn't have to be between two of us. It could be A to B and B to C and C to, but eventually there could be some kind of a situation where the from and the to are relative, are depending on what the data is, and they could be the same data. But what if one person tries to transfer money from account A to account B, while another person tries to transfer B to A? Exactly my case. So that the from here will be, like I said, the from here is me, but his from there is him. And now I'm about to go to the two to get him. I can't. So we have a deadlock. So even this, which looks great, is a problem. And there's no easy answer to that.
And he can't release it because he doesn't get there because you've also locked yourself.
Well, he just comes to this code, to this line of code, acquire one, he succeeds. Then he comes to acquire two, and he waits. He doesn't know. How should he know that you're not going to release it? How does he know that you're waiting for me? Maybe the one he's trying to send to is going to be free in a minute. So he just waits. How is he supposed to know? Especially if it's a distributed system. In other words, this system, he doesn't necessarily know what's going on the other side of the world. Okay. Deadlock avoidance. So that was deadlock prevention, yeah? We prevented it by imposing, one solution was imposing a total hierarchy. We prevented it, can't happen.
We don't have.
Or I came up with a system of preemption, where the minute I'm waiting for somebody who's waiting for somebody, I just preempt it. What? Question?
We didn't have a solution for the transaction one, it's just.
No, I didn't have a solution, just pointing, I don't have a solution.
You could have an order, you could have like the absolute order of accounts, right? You give each account
Yeah,
number
yeah.
by the ID, and then you take that lock first, the lower ID first, always.
Yes,
You have to
good.
check
Actually,
out-
there is something called IBAN, which is the International Bank Account Number. IBAN, International Bank Account Number. And there's one, like my bank account has one number that nobody else in the world has, and your bank account has one number. So I could just say, but how would I know that you're over? When I'm going, I'm smaller than you, so I get priority.
Right.
But how do you know on the other side of the world that that your number is lower than mine?
Every time you always get two accounts, it's like you always just try to get the lock
Yeah.
first. Right? There's no solution.
Oh, I see what you're saying.
Because you all have to know.
You're saying, no, but what if I'm waiting for you and you're waiting for, what if I'm waiting for, A is waiting for B, B is waiting for C, and C is waiting for A? So. I would still work out like that?
I think that's what our solution was, right?
Yeah,
And start
Yeah, that
QR.
was a solution. Okay, you have me convinced. In other words, you're just saying, it won't always be from and to, it'll be lower number, higher number. And so when I'm trying to send, I look at my number and I'm number one and he's number two. So I'll do even though I'm sending to him, so I'm sending to him, so my from is one, I'll do my from first. But when he's trying to send for me, he says, I'm gonna do not the from first, I'm gonna do the two first, because the two I'm trying to send to a lower number. So he'll do the two first. And then he'll try to lock me, and he won't even lock himself, and he'll wait on locking me. So he'll get the money before he sends me the money. That would work, yeah, using the IBAN, but you have to have some kind of international standard.
That could be tough.
Okay. Data avoidance, so that's all prevention. Now we're talking about deadlock avoidance. It's in other words, we're going to.
This is where we're gonna let it happen.
No.
But detect it.
Avoid, no, this is even worse, even more. That was prevention, that means like. You don't let it happen. Now what we're gonna do is we're going to, it's also kind of prevention. We're gonna prevent a situation where a deadlock could happen. We're not even gonna prevent deadlock. We're gonna prevent a situation which could lead to deadlock. So we're gonna, it's even more, we're avoiding it. It's like midavar sheker tirchak. We're even going further. We're not just not doing it. We're not allowing it to happen. We're not even getting close to letting it happen. And somehow this is a little bit easier. Well, I don't know, it's a different thing. I don't know if it's easier. I want to say it's easier, but let's see. All right, requires that the system has some additional a priori information available. For example, the number of resources that I will possibly want. In other words, if I know somehow that no Word program will ever want more than one printer. So I know it's going to want one printer, and it's never going to want more than one, 2 CPUs. I don't know. Whatever the number is, I know somehow this program, what its maximum theoretical usage could ever be. That's the a priori information. The simplest, most useful model requires that each process declare the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there never can be a circular wait condition. Resource allocation state is defined by the number of available allocation resources and the maximum demand. So let's see, really we need to see an example. There's something called a safe state, which is important. When a process requests an available resources, the system must decide if the immediate allocations leaves the system in a state that is safe. In other words, if I give you something, it's not going to cause a deadlock, but it's going to put the state, the system in a situation where a deadlock could theoretically possibly ever happen. Therefore, I won't even give it to you now. It's kind of, this is also called the banker's algorithm, because it's kind of like the banker always keeps a certain, this is the way I understand it. The banker always keeps a certain amount of money in his drawer. He doesn't want to get in a situation that somebody asks for money and he can't give it to him. So it's like the cash machine says you can only ask for up to 5,000 shekels. Because if you would allow you infinite, then it could have a situation where you took out all the money and then nobody can do anything. So you sort of keep a reserve. That's the idea. It's really hard. I'm going to skip this words because it's hard to understand with the words. Yeah, let's go to this. Well, first of all, the idea is like this. Deadlocks occur sometimes in an unsafe state. An unsafe state is not equivalent to a deadlock, but deadlocks will occur sometimes. Safe states can't have deadlocks. Unsafe states could have deadlocks. Okay, so here's an example. Let's say I have 3 processes and he needs, let's assume that just one resource. And he needs potentially 10 of them, he needs 4 of them, and he needs 9 of them. And the current use is 5 and 2 and 2. So that means that his future possible needs, because he's currently using 5 hard drives, but he could potentially ask for 5 more. And then he'd be at his maximum, but he couldn't ask for 6 more. So we could actually make a third column called need, which sometimes we do, which would be the difference between the subtraction. We do the maximum minus the current use, gives me the need. That's what he could potentially still left for him to request. And here the need would be 2. He still could use 2 more. And maybe he'll never ask for 2 more. Maybe he's already used the 4 and he's now going down to only 2 and he's never going to get to 4 again. Or maybe he'll never get to 4. But he could potentially want 4. And here he could potentially want 7. So if we have 12, it says here, what? Suppose we have 12 disk drives. So if we have 12 disk drives, how many are available at the current time? Simple math here.
3.
3. 12 minus 9. 9 are in use, there's 12. So there's 3 left. So could we satisfy so the question is like this, are we in a safe state? Well, the way you would determine is like this, you can't give him his needs and we can't give him his needs. So it looks like no, but maybe not, because how many did we say there are 3 available?
Yeah.
So if there are 3 available, then as long as we don't give this guy anything, and we don't give this guy anything, and then this guy could potentially ask for 2 more. Let's say we'll say like this, we'll never give this guy any more and this guy any more until situation.
One more.
Well, let's say we won't. All right, fine. We can give 1 more. But you're right, I'll give him 1 more. You're right. But I'll give him, let's say, I'll keep my 3 on as reserve. And then if this guy ever asks for them, I'll give it to him, actually. I will grant it. And then I know for a fact that P1 will eventually finish. Because we're assuming that all programs finish. So when P1 finishes, he'll release the 2 that I gave him or I didn't give him. Maybe he'll never ask them. But he'll release the 2 that he's got, which will give me a reserve now of 5. With that reserve of 5, I can now start to let P0 grant him his requests. So now if he gets his requests, and I won't give him his requests, because if I would give him his request for 5, then I could get that he'll ask for 1 more and I can't give it, or he'll ask for 1 more and I can't give it. So I'm not going to give the 5 to this guy, but to this guy I could give the 5. So this guy will be frozen again. And I'll keep all the 5 on reserve in case this guy ever comes. And if he comes, then I'll grant him the 5 and then he'll finish. And then I can let P2 get anything he needs because I've got now 10 resources. So what we could say is like this is a safe state because I can work out logically an order by which I can grant the requests of the processes such that everybody will get their maximum requests. There is I could say like this, there is a path. There is a path to victory, a path to solution. If there's no path, then the state is unsafe. And it could be even if I had reserve, it's still an unsafe situation. For example, if I had a reserve of 1 here, I have a reserve of 1, but it's not enough to create this that wouldn't be in a safe state. Now, is there a deadlock going on here? If it wasn't 12, it was 9, and not 9, 10, and I had a reserve of 1. So this situation is unsafe, but is it deadlock?
Not necessarily.
No, it's not a deadlock. So that's what we're saying. We're just declaring that this situation is unsafe, and we would never let us get there. We would even prevent, it would never even gotten so far. We wouldn't let ourselves into an unsafe state. That's the idea. Even though there's no deadlock. So this, of course, this is a problem. What's the problem with this solution?
Oh, it's underutilized.
What?
So it's underutilized.
Right, the system will be underutilized. We'll have resource utilization will be low. We'll have always keeping reserves that we may never get used. And this poor guy comes and says, I want 1, I want 2 more, and we won't give it to him. We'll give him 1. Like you said, we give him 1 because if we give him 1, we'll still have 2 left over, and that's enough for this guy. So you give him, but it's not. Actually, we
We
won't.
wanna give the
We
P0.
won't give him 1. If he asks for 1, we won't give it to him. Because then if we have only 2 left over, this guy could finish and we'll have 4, and that 4 is not enough for him or him. So if this guy asks for 1, we won't give it to him. But if this guy asks for 1, we would give it to him. Because this guy can ask for 1, and now he can still ask for 4 more. And then this guy could ask for his 2, and we could grant it, and then he'll finally finish, and then this guy will get everything.
Really, this solution is just giving them resources before they ask for them. They're just like,
Well, it's keeping them on reserve because you're
Right.
saying, no, because if this would be 5, this would be 5. Right, it's sort of like we're giving to, but theoretically you could have 2 processes that are, what if you had 2 processes that were 4?
Okay, yeah.
Then I could choose,
Yeah, then we could choose.
then either one could get it.
Whoever asks for it can get both.
Right,
You can't give 1.
You can't give 1 because then.
well, if there's 3 left over and there was 2 with 4 or 2, then I could give 1 to one and 2 to the other.
Yeah.
Because the 2 that I gave to would eventually finish, and then the 1, right, so it's not that I've actually allocated it, but I've kept the reserve, and it could be, yeah, it's a good point. I could actually, I mean, my answer to you was a good answer.
Yeah.
Because I'm saying, there could be a situation where I It's not like I allocated it to him. It's available for anybody who's in that circumstance. So if we go back to what I skipped, I think it just says, we have, let's just read what it says here, so we get it right. A system, let's see if it makes sense now. A system is in a safe state if there exists a sequence, P1 to Pn, of all processes in the system, for any Pi, the resource that Pi can still return to be satisfied by currently available resources plus resources held by. Yeah, it's basically the same what I'm saying, as long as it's a path. All by Ij, where J is less than I. In other words, there's some kind of path that will lead to it. That is, we have a safe state if Pi resources, if Pi resource needs, no, if his resource needs are not immediately available, then Pi can wait until Pj has finished, because Pj is less, right? If Pj is finished, when Pj is finished, then Pi can obtain the needed resources, execute, and return the allocated resources and terminate, which means he's finished now. And then when Pi terminates, Pi plus 1 can also obtain his resources. No, you're just explaining what I said. That is a path. Okay. One assumption we make is that after a process has its max needs fulfilled, it will finish. Is there a scenario in which we process? Is there a scenario in which processes request their maximum needs and we can fulfill these requests one by one? Yeah, could be their requests, their maximum needs, not in this case, but. Well, he could request one, yeah, he requests maximum, right, that's, in other words, that's the question that we're asking ourselves. Is there a scenario in which the processes request their maximum needs and we can go by order, and we have some order by which we can fulfill them? Example continued, if P2 is allocated one more disk, will we be in a safe state or not? If P2 is given one more disk, will we be in a safe state? Right, that was the example I gave. Theoretically, you say yes, because P1 will finish, but the 4 is not enough to finish P0. So if P0 asks for one more request, we can grant it. Okay. Avoidance of a single instance of a resource type. So here, how are we going to avoid deadlock? One way is if we have single instances, we can use a resource allocation graph. And obviously, that graph will have to be, well, you learned in data structures how to build graphs in software. So you'll build a graph in software and you'll look for some kind of link. But that's only if you have one single instance. Because if you have double instances, we said that sometimes there could be a circle and it's still not a deadlock. Or you could have multiple instances of resource, then you should use the banker's algorithm, which is what we call this. Because that will work with these multiple numbers, like 10, like how much he needs. Okay.
The banker's algorithm is not the baker's algorithm, so it's different.
Exactly, it's very confusing. We learned already in the lab, we learned the bakery
I was
algorithm.
thinking the bakery.
And there's a banker's algorithm, it's a different thing. Maybe we should rename it. I think we did rename it the Delia algorithm and the banker's algorithm. They're two different.
Baker's one is the transaction we just saw.
What we just did was bankers. It's like, right, and the other one is called the bakery algorithm or the deli algorithm. Flame edge. Resource allocation graph scheme. If P of J is pointing to R of J, indicates that the process P may request resource J, represented by a dashed line. Again, let's go to the picture here. Right. With this, so what's the difference here? What does this mean? This means that, what does this mean? This means that P1 is using resource 1, right? And P2 is waiting for resource 1. And there's also resource 2 over here. Now the question is like this. If P2 would ask for resource 2, should we give it to him?
Why not?
It's available.
Yeah, he's waiting for it, why not?
Specifically, you may.
No, because then P1 may ask for it also, and then we'll have a loop. If we would grant this, then the arrow would be pointing the other way.
Oh.
And then this code could eventually, this dotted line means that he's not asking for it, but he may ask for it in the future. So we don't want to grant P2 this and turn this into a solid line pointing the other way, because then we'll be in an unsafe state, because then even though we don't have a deadlock, we could get a deadlock because he could come and ask for this. We want to avoid a deadlock. So but we would, if P1 would ask for the resource, we would grant that. Because P1 anyway has already got resource 1 and he can give him resource 2, and what's the problem? So this is kind of like this is the bakery's algorithm. This is the banker's algorithm. This is the banker's algorithm, but graphically. And that's what we were saying. You can do the banker's algorithm graphically if you only have one element, one resource of each type. In other words, so you understand? So in this case, it's a safe state, but request by P2 for resource 2 cannot be granted. But request by P1 for resource 2 could be granted. Because then he's got everything he needs. And so that's going to be totally safe.
Unless P1 finishes, then we can grant.
If P1 would finish or release, or if P1 would release resource 1, then we could grant P2 in this resource 2. But in the current state, we can't grant. And we call that a request edge is converted to an assignment edge, right? That's what it says in the previous slide. That's when that's when this turns into the other way, when the actual this is called a claim edge. If you want the terminology, which you should know, a claim edge converts to request edge when it presses request. So in other words, if P2 would actually request R2, then this arrow would become solid. If the request would be granted, then the arrow would switch directions. So it's 3 states of an arrow. It could be a claim, an actual request, or a granted request. That's what this previous slide said here. Here it says resources must be claimed a priori in the system in advance. So what about this situation? Here is the request granted. And now P1 may request R2, which we call a deadlock. So we don't want to get into this situation in the first place. Because we know that we know something about P1, that he may someday request this.
Here, so the R2, sorry, P2 is an instance of R2 or that R2?
P2 is a process, R2 is a resource.
So resources being. Okay, so I guess I'm confused by the direction. For the change of direction, change the direction because.
We said that before, that was just like we did before,
Yeah.
that the resource, when it's a request, it's pointing. And when it's allocated, it's away from the resource. You think of it like an anchor.
Okay.
This is the heavy item. This resource is like a big boulder, and it's connected. It's actually connected to the arrow. This is he's pointing, not connected. He's just pointing to it. So he hasn't gotten it yet. He's just requesting it.
Okay.
The switch is when he says, "I want to actually be connected to it." Okay, that's what I think of. Resource allocation. Suppose that process PI requests resource J. The request can be granted only if converting the request edge to an assignment edge does not result in the formation of a visually discernible cycle in the resource allocation graph. In other words, here there's no circle, so it's safe. Here, there is a circle, so it's unsafe, even though it's not a deadlock. Now, if I would have granted P1's requests, then if P1, then the arrow would switch and also would be a circle. In other words, this is a problem because we have a circle, even though this is a dotted line. Again, this is not that would be an interesting question to ask on an exam. Is this a deadlock or an unsafe state? I mean, that would be a very easy question, but this is not a deadlock, it's an unsafe state. An algorithm for detecting a cycle in such a graph requires n squared operations. That's what I was saying before. In other words, to actually build this graph and then run through it, you have to check every node, is it, you know, is there a circle based from him, you know? You have to check, is there a circle in any possible way? So there'll be n squared checks. Banker's algorithm, so multiple instances of a resource. So now we're going back to the Banker's algorithm. This is the actual algorithm for it. So we have multiple instances of a resource. Each process must aperiodically have maximum use. When a process requests a resource, it may have to wait even if that resource is available in the system. When a process gets all the resources, it must return them in a finite amount of time. That's pretty much what we've said. All processes eventually end. So let n be the number of processes, m be the number of resources. So n is process, m is resources. We'll make a vector of length m for the resources. If available j equals k, then the total k instances of resource of type R in the system. Basically, we're making a vector of m times n, this large array. And here, the need is equal, you know, the need of each is equal to the max of each, you know, each process per resource minus the allocation of each process per resource. This is just a mathematical way of saying the following. Here, I'll skip this. Here you see just the loop where we have to go through. Anyway, let's look at the example. The example is where you can understand it. Suppose we have 5 processes P0 through P4, 3 resource types. For example, the resource A, B, and C, and we have 10 and 5 and 7. So how do we know there are 3 A's available? Well, we had 10 A's. Why are the 3 A's available? Well, if we count up all the A's of all the P's, we see there's 2, 3, 2. 2, 3, 2 is 7. 10 minus 7 is our need, is our available. So the 3 makes sense because it says here 10. And why 5 instances? 5 instances of B. Well, B is using 1, 1. And that's 3 and plus 3 is 5. And C is 7. Well, he's using 5 and there's 2 left over. Okay. So this all makes sense. But now we have this max. We didn't calculate the need, but the max, you know, is the system in a safe state? We want to determine now, is the system in a safe state? So it's the same thing we did before with one resource, except we're going to have to check every resource at the same time. So for example, is there anybody who we potentially could fulfill? Yes, P3. We could potentially fulfill his request because he only needs 1 more of B and 1 more of C, and we've got them. Could we potentially fulfill P2? No. What about P1? Yes. You definitely could fulfill him. What about P0? No. So P1 and P3, they're the most modest requesters. We can fulfill them. So we want to see if the system is safe, which would mean, can we get out of it? Can we finish up all the processes, given what we have? So I think we can. Let's see. If we grant this guy's all his requests, which we said we could, because 0 minus 2 is 2, we have 2. And 0 minus 2 is 2, and we have negative whatever, it's 3, we could do it. And here that was missing is only 1, and we have a 3 here. Okay, so we could fulfill it. Now let's imagine that we fulfilled it. Actually, do I have a marker? I have a marker. I'll show you how you do this. Yeah, I have a marker. Stop share. And I don't think anybody can see it. Oh, stop share. But I got it over here. And. Okay, so what do? We say it like this, let's take P2 because he's gonna give us, or let's take P3. Let's take P3. P3 we can fulfill because there's available. So we can change our available now. We can say P3 we're gonna grant him. And therefore he's finished. We've granted him his requests. As everybody else will say, we're not gonna grant you a request. And we're gonna wait for P3 to finish. Because we have enough to fulfill his request.
So we're at 5.
So now we can add 2, 1, 1. 2, 1, 1. So we get 5, 4, 3. And that's how much we have. Now with 5, 4, 3, we can definitely fulfill P1 for sure.
Fulfill it.
So let's fulfill P1 and we'll add a 2 over here. So we get 7, 4, 3. And now with 7, 4, 3, we could definitely do P4. So
we can do everyone.
yeah, so wait, so what was our order? Our order was 2, 1. No, 2, where do we do 3? We did 3
We
first.
did 3 first.
3, 2,
There one.
1, 4. And then 4 will give us 2 over here, so it'll be 7, 4, 5.
We can do 0.
And we can do 0 because we have 7. We have our 7, we have our 4. So we can have this order. So that would be our proof that that would be the correct order or a correct order. There's more than one correct order. I could have started with P3 or P1. So now we can pronounce by this whole thing we just did now is an algorithm. And that was what I just defined in the slides before. Sort of defined it in, it's a little bit complicated to explain it, but it defines what we just did. We basically found a path such that we can fulfill all the requests and then we can give back those resources to the system to allow more requests to be done. Now, the question is, how brutal did we have to be? Could we have granted any requests along the way? In other words, let's think of something, for example, let's say that let's say, for example, that P0 requests 1A. At this point, we're in a safe state. We've proven this is a safe state. Now comes along P0 and he says, please give me 1A. So he wants to change this to a 1 and change this to a 2. Will we still be in a safe state? Well, we can still fulfill this guy
And P1.
and P1. So we can add. Wait, can we? Yeah, right. Yes. Okay. So we can add 2 here. And what'd you say? And P1 we can finish. So we can add 2, 1, 1. And so we'll get 3, 4, 6. 6, 4, 3. And now we can actually fulfill this guy. So yeah, this is a safe state. We've already proven if we can fulfill this guy, then we can fulfill everybody. So we could grant that request. But there might be some requests that we can't grant. For example, if he would ask for 2 and change this to a 2 and this becomes a 1, then I don't think we could grant that request. Because with 1, 3, 2, we cannot fulfill.
We can fulfill
Oh,
what?
we can still what?
Still do it.
We still do it?
Yeah, you can still fulfill.
Because-
3, then.
Right, because he doesn't need any, he just needs 2 over here.
Make it 3.
Okay.
Make it
And also
3,
P1.
0 or 0, 3, 2.
Anyway, you see that there could be requests that we couldn't fulfill. There definitely could be requests that yeah, exactly. If he would request 2 over here, 2 more over here. So then this would be,
Or if you request 3A.
change this to
1.
1. So now it's 3, 1, 2. Well, we could still do this guy.
Go to P3.
Just change A to 3. Change
And
P0
P1.
A to 3 and it's impossible.
Say it again, change.
P0 A to 3. making a request.
Well, that's for sure, yeah, that's for sure. But I'm trying to find something that's more small, but yeah,
If he asks for 2 Cs. Or really once.
well, if he asked for one. If he asked for one and he asked for whatever, you see that there's obviously requests that can't be fulfilled. That's the point.
Yes.
Okay. Back to. Well, here they just did, the slides just sort of do what I did, which is we created a need here. In other words, we created a need table. Here his need was 6. See how it's, what is his need for P0? It's 6, 4, 3. Because it's whatever he hasn't gotten yet. 6, 4, 3. So that's what it says. Wait, P0 is 6, 4, 3. Why does it?
7, 4.
That's a mistake, no?
He starts off with 0 in A's.
Oh, 7, sorry, 7, 4, 3. Yeah, sorry, my mistake. 7, 4, 3. So it's 7, 4, 3. And you do that for all of them. The system is in a safe state since the order 1, 3, 4, 2, 0 safely satisfies safety criteria. Okay. Safe state path to solution, and here it shows exactly what we just did. If you start with P1, then the available all of a sudden becomes 5, 3, 2, etc. You see the available becomes larger and larger. And you can fill everybody's needs. So let's check that the request is less than or equal to what's available. That is, for example, what if P1 requests 102? Go back to over here, P1, he says he wants 102. Well, that's less than his max, so he could ask for that. 102. The 2 over here is gonna be the problem, right? The 2 over here that he's requesting is gonna take away all of C. And that means that P3 will have a trouble. And P1 will have trouble.
No, P1 won't have trouble.
P1 won't have trouble? Why?
We can still do P1.
Why? But he needs, if we took away all the C, how can we do P1?
Oh, who's requesting? Isn't P1 requesting?
Oh, right, good point. Where was I?
Yeah,
P1, right, since it's P1, it can still, exactly the trick question, as he himself can be finished, and then we can grant it. So anyway, check that the request that is 102 is less than what's available. Yes, it is, it's true, that's the first check. Then pretend the request has been granted and create a new table. So if it would be granted, P1, we would have 0 over here. You see the C became 0. Are we in a safe state? Yes. Executing safety by P1, like you said, we start with P1. Then as we finish his request, since he was the one who asked for it, in other words, if P0 had requested 102, it wouldn't have worked. Because that would have, then there would be nobody because everybody needs some Cs. And we've emptied out the Cs. Everybody needs some Cs. True, let's see. No, actually P3 doesn't need any Cs. But he needs another A. He needs one more A. So anyway, yes, we can request 330 by P4 be granted. P4 wants 330. So 330.
Are we doing it from the previous table, I think?
Yeah.
Not from here.
Yeah, exactly. 330, we've got it available.
But
So
I think no. I don't know actually.
P4,
No.
330.
Not this table, not this table.
I know, but still, 330, I'm just remembering,
Ah,
this 330 will mean that the C will still be 2, but these will be zeros.
can you do anything with just the C?
No.
So P4 himself, 330, he still wants one more A, so he can't finish. And he could, wait a second, there's no, right, the C doesn't help him. The 1C doesn't help him.
Yeah.
The 1C doesn't help him.
It doesn't help anyone.
It doesn't help anybody, so no, you can't be requested, see, the one C that we have left, or the Cs that we have left over is not gonna help. Can request. For 020 by P0 be granted. So he's asking for all the B, he's asking for 2 of the Bs.
Yes.
So I said P3, I guess I should, yes, it's safe, okay. All right, let's stop here, we'll go to Mincha, and we'll continue after. Okay, so. Okay. So there's also deadlock detection, we talked about avoidance, prevention, detection. Allow the system, is another idea, allow the system to enter deadlock state and then detect it and then try to recover from it. So we'll have also a wait, we'll also have a graph. No, which is called a wait for graph. Nodes are processes. If process I is pointing to process J, if process I is waiting for J. So in other words, we're not interested in the resources, we're kind of removing the resources from the system in a sense. And we just have a graph of the processes that are waiting for, who's waiting for who. Periodically invoke an algorithm that searches for a cycle in the graph. In other words, we'll keep track of which processes are waiting for which. And then we'll periodically check, is there a circle? Then there's a deadlock. An algorithm to detect a cycle in a graph requires, again, n squared operations, where n is the number of vertices in the graph. So for example, if we had a situation like this, where this is a resource allocation graph and a wait for graph. So here's the resource allocation that we've seen before, where we have the resources and that the processes are waiting for the resources, but we now are going to convert it into a corresponding wait for graph, which only has the processes in it. So you see from this that process 1 is what is he doing? He's waiting for this resource, but this resource is held by process 2. So that means he's essentially waiting for process 2. That's what we draw over here. P1 is waiting for 2. And P2 is waiting for a resource, but it's held by P5. So P2 is waiting for 5. Now, if that would be the only situation, we wouldn't have a loop. He's 1 is waiting for 2 and 2 is waiting for 5, and there's no circle. But 2 is also waiting for resource 4, which is held by 3. So he's just waiting for 3. And 3 is waiting for 5, resource 5, which is held by P4. So P3 is waiting for P4. And here we have a loop. So when you have a loop, we actually have, I guess, 2 loops, but we have a loop.
3 loops.
Even 3. Well, the outer loop and 2.
Yeah, the big one.
Okay.
I mean,
What if you have
Okay.
several instances of a resource type?
this is.
So we have to have a 2-dimensional array again.
That way.
This is just the algorithm, which you can look at in your times. Okay, algorithm requires an order of O to the m times n operations to check whether the system is in deadlock state. Now, there's a lot of checks if we have multiple resources. Example of detection algorithm. So it's kind of similar to what we had before. Here we have a system, no available resources, okay? I guess that makes it easier. No, but we don't care about available resources. We just care about, is the system now in a deadlock, right? So it's kind of makes sense. They gave us 0 here. 5 processes, 3 resource types, and 7 and 2 and 6 instances. So this is not in a deadlock since sequence P0,
And P2 can just go.
right, allocation request, see, P0 has nothing left. It doesn't mean that necessarily it's not in a deadlock. You have to then look at the. Well, wait a
I mean,
second.
it has all it needs.
No, it could finish, but the other ones could still be in a deadlock.
Well, the other ones maybe, but they
Yes.
can go.
That's
What about this guy? Why can't, so P0 then P2?
Yeah.
P2 also has nothing.
Yeah.
So, okay,
So they go, their release is 313.
Yeah,
Then
313
P1
you could
can
obviously
go,
do everything.
or
People want at most 313 you could do.
and any other one can go after that.
okay.
It's not deadlock.
P2 requests an additional instance of type C. Well, there is nothing type C. Is there currently a deadlock? Oh, so he requested it. We're not asking the question, do we grant it? Because we can't grant it.
Mhm.
But did that request itself cause a deadlock? Because he's not waiting. So again, what is the question? P2, was he in our list? P2 was actually the second one.
They changed things around.
Yeah.
Oh, they changed things around?
Two is now requesting one in C.
Oh, okay. You know,
It
it's
says
the same,
zero.
same list, sorry. It is.
Same list, but P2, his allocation was 303, and
And
now
it's-
his allocation is 3, but he has a request of 1.
So now you can't, it's.
No, it's deadlock.
Deadlock.
Why?
Because you can
Because
only
B0
finish
goes,
with 0, and then
and
you
you
only
get
have
one
one free thing, but no one wants a B. B doesn't help anyone.
Yeah.
What are you saying? He requests another. He requests another C, right?
But there's not a-
And there is no other C.
The only thing we have is a B.
So the question is, can other people finish before him?
No, because they're all requesting something.
They're all requesting something except for him,
And he only gives a B.
and he only
No
gets
one wants
B, and he doesn't even want to be. So is there currently a deadlock? The question we have to ask ourselves is, can reclaim resources held by process P0? We can't, in this case, we can reclaim the resources held by process 0, but they're insufficient to fulfill other process requests. Deadlock exists. What is the deadlock? P1, 2, 3, and 4. When and how often should we invoke this? In other words, we may never get a deadlock. We may not, I mean, if we invoke it a lot, we'll have to be wasting O of m times n squared. And that's a lot of energy. So how often the deadlock likely to occur? How many processes will need to be rolled back? One for each disjointed cycle. In other words, we may have to break a lot of processes, and that's not fun. It's not easy to do. If detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and so we would not be able to tell which of the many deadlock processes cause the deadlock. In other words, if this, we have to choose somebody to break, right? We don't know who is the best one to break. Recovery, and also the problem of recovery from deadlock process termination. In other words, we had the deadlock processes, so now we're going to kill some process. So we have to recover from that. So one thing is you could just kill everybody. And then you'd have to restart them all, but then that could cause it all again. Abort one process at a time. So I think that actually the deadlock is consisting of these three, but it's like maybe if I would look over, let's look back at that picture that we had here. You see, if I would get rid of, look at this situation here. P1, 2, 3, and 4 is a deadlock, right? He said there's a deadlock. We have detected there's a deadlock in 4 processes, but we could easily kill, for example, P3, and we would still be in deadlock. So that's what he says. You have to start randomly. You don't know. We haven't detected actually who is the one that is the essential one. Like obviously, we should get rid of P2 would be the best one, maybe,
Or before.
or P4, because they're the ones that bring it back, right? So what we'll do is we'll start killing processes until, and then run the algorithm again and see if we still have deadlock. And we don't really know. So that's what it says here.
It's like M to the 4th.
Abort one process at a time until the deadlock cycle is eliminated. In which order should we choose to abort? So who should we choose? We could have priority of we could give higher priority processes, we could not abort them. How long the process has been computing? We could do long ones, or we could do shorter ones. Shorter ones, what's the advantage to killing shorter ones? There's less work that we are losing, because if we kill it, we have to start it again.
Can we just always kill the one that started the most recently? Because then that's what caused deadlock.
Not necessarily, because we don't really check them periodically.
No, but if we have it when each process started. Then
No, but again,
oh, I guess
no,
no, added to the
no.
cycle. not
Because of
when it's-
multi-
it added to the cycle, exactly. There was,
Yeah.
it joined in. It could have been that, like back in our picture over here, the most recent process could have been P3. He's not really causing the deadlock, he's adding to the deadlock. So wait, what did I say here? So how long is the process computing? Resources the process is used. We could kill the ones that's using the most resources. That's also probably gonna help. Resources process needs to compute, needs to complete. Not how much he's using holding, but how much he is requesting. His requests also cause the deadlock, right? Your holding is causing deadlock, and also your requesting is causing deadlock. Remember, we have that concept of hold and wait. So either of those things, either of those criteria can be reasons. How many processes will need to be terminated? In other words, we could try, obviously, want to choose the one that will have the least amount. Is process interactive or batch? The batch file, that means it's not so urgent, we could do it later. So selecting a victim, we want to minimize the cost, select the process that is not close to completion. Right, it'd be a pity to kill somebody who's just about to complete. Select process with many resources, so preempting it will help many others. Or select with the fewest resources, since less preemption will be required. I guess it's to actually, it's not using so much, so we don't have to do too many preemptions. Starvation, the same process may always be picked as a victim. So we include number of rollback in cost factor to try to make different victims selected each time. In other words, we could have a rollback count. How many times has this process been rolled back? All right, that's it for deadlock, but let's go on a little bit.
How much time do you have?
We have time,
No, I don't know.
so. Recording. And we are now in. Chapter 8. Current slide should occur here. Okay, so now we're actually in a more complicated subject. That was sort of a light distraction. So we're talking about memory management strategies, which means how do we allocate the memory? We have one memory or RAM, and we want to allocate it to all the different processes in an efficient way that everybody can find their memory. When I jump to a new line in my code, I get to the right line. How do we know where it is? Because remember, there's many programs, they're not, if in MIPS, I thought that my when I was writing in assembly, I thought that my line of code was at line, let's say 1,000, and the next line was at 1,004. But really, when we put the program into the memory, it might be in a totally different location, because we can't put everybody at 1,000. And every program, let's say, starts at 1,000, they can't all be at 1,000, so they all going to be different places. So we have to have a method for mapping the logical address, the address the program thinks about, to the physical address, the actual address. We talked about this. It's called address. I remember we didn't mention it a little bit in the beginning. Address binding. One way is that we do it statically at the beginning when we load the program into memory. We change all the numbers. We could just throw this guy into location 4,000 and change all the thousands to 4,000, 4,004, just change them and it fixed. And then we load another program, we'll put them into 8,000, we'll just change all the numbers. That would be static. That's one strategy. We'll see other strategies. Okay, program must be brought from disk into memory and placed within a process for it to be run. As we have to create a process for it and let it run. The main memory and registers are the only storage the CPU can access directly. You can't, in other words, we can't run, what's the point of that line? We can't run the program from the hard drive. We have to put it into main memory and then into register. Memory unit only sees a stream of addresses. There's read this address, read requests, or address and data and write requests. It just knows an address. Registers register access in one CPU cycle or less, right? When you want to access the register, it's the fastest thing you can do pretty much usually, and that's one cycle. Main memory can cause many cycles, can cause a stall even. We saw this in the pipeline. If you want to do pipelining, then if you do a memory, we didn't really talk about that actually, but we sort of assumed that you could do a memory read in a single cycle, but you could imagine where the pipeline steps are very small. So instead of having 5 stages, you have 32 stages. So then the time for each one is much less, and maybe you can't get a memory read in there if maybe take 2 cycles. So that's causing a stall. Cache sits between main memory and CPU registers. So because of the slowness of memory, we want to bring as much of the memory into cache so that we can access it faster. Protection of memory required to ensure correct operation. Protection would mean that I shouldn't access, one process shouldn't access another process's memory. Okay, so here's this one idea where we don't go in and change the program itself, but we do something, we use something called a base register and a limit register. The base register is where in memory this process starts, and the limit register is how far it goes. It's not the end, it's just the distance. So there, a pair of base and limit registers. The word register is very important here. What does that tell you?
There are many.
No, what else does it tell you? There's two, base and limit, but registers. What is a register?
Part of the CPU.
Part of the CPU hardware. In other words, it's not that the operating system keeps track of it. It's in a register. Now, when a certain program is running, the operating system has to load the base and limit registers for that program. And then every subsequent memory request, the hardware will automatically add this number to it. Because if I say 1,000, or if I say 0, it'll add this number to it. And then if I say, it'll add 300,040.
Yeah.
If I say 4, it'll say 300,000, but the hardware's doing it.
What's the point of the limit register?
So it doesn't go too far.
So there's a
The
type of
hardware will prevent me. If my program says jump really far ahead, the hardware will give an error, will give an error. The CPU won't. CPU will say, do whatever you want. This is a way that the operating system can control where I can get to. But some students mistakenly think, oh, this is in the operating system keeps track of that for each process. It's true, the operating system does keep track of it for each process, but it needs to load it into those registers. Otherwise, every time I would do every memory check, I would have to go into the memory of the operating system and see what's held there. And that would be slow. I want to put it into a register. So this defines the logical address space for a given. Oh, a pair of pages define the logical address space for a given process. Only operating system can set these values. Right. In other words, only operating system. You have to be in kernel mode to change these registers. I'm not sure this is correct. Maybe it is, but I would prefer to say physical. This is the physical address. In other words, define the physical address space. The physical address space is from this point to here. That's where it is. The logical address space we usually say is the way the program looks at it. The program thinks he's going to address 0.
Right.
And comes along this base register and adds a number to it and puts it in somewhere else. So here you see, so I'm not sure why it says logical. I might have said, it's probably written that in the slide, but there may be a new version that changed it. But maybe it's right. Maybe I'm understanding something, but I would change it to physical. Special fast hardware in the CPU must check every memory access generated by in user mode to be sure it's between the base and limit registers. In other words, if you're in kernel mode, you can go anywhere.
Yeah.
But if you're in user mode, then there's special hardware that's going to check every time you do a memory access, it's going to check these registers.
This is between, it's not that it adds the base.
It adds the base. Well, if I say 0, then it's actually here. It adds the base. We'll see. It adds the base. The limit, it
It doesn't
just
say between the base and the limit. That's the weird wording. If it's adding the base.
no, it means that make sure it's between those. After I've added it, is it still between them? It should mean as it should. Well, it could have been that I said go to address -5.
I guess.
Okay, so you see here, but also you notice here that the operating system occupies some space in the memory. And then here are each processes, they're each divided up. And this is a very static kind of way of thinking about it. The program, that's its memory, it doesn't move from there. You put it in, it lives in that space, and that's it. So here's the diagram showing what we do. We take the CPU address and you know what? I'll take it back. Let's go back. Before No, before, I remember I said I had a problem with this.
Yeah.
Logical, it really does mean logical, and I'll explain why. Because we're not really getting to the point where I said, what I said is that you add it. And that's what we'll see that in the next couple slides. But first, we're just saying, no, imagine that at load time, the loader changed my addresses. Remember I said that we could also do that?
Yeah.
The loader could just change the address. So he changed the address of my thing to be within this range. So now I'm just there. So it is my logical address. I've changed my logic. When I programmed it, I wrote 0. I wrote go to line 0, but the loader will change it. So now the new program that's been created by the loader has different logical addresses, and it's in this range. And then this diagram makes sense, because then I can say every address will actually now be to that location. And I'll check, is it greater than the base? If yes, then is it less than the base plus the limit? And if it is yes, then I can go to the memory. And in any case, if I gotta know, I have it tracked to the operating system, some kind of interrupt. I've gone to some. So that's the first idea, is that this depends on who's doing the changing. If the loader changed the address, then now my logical address is different. And so therefore I'll just check. But now we're gonna talk about address binding, which is, I love this term, address binding. Because it sounds very like what does that mean? And yet you will know what it means.
Mysterious.
Program on disk. Okay, there's a program on disk. It's ready to be brought into memory to execute from an input queue. Remember that a scheduler may have put a process on the disk in order to decrease multi-programming. So, right, it could be that there's a program that is outside of the memory, it's on the hard drive, and it would like to run, but we're not letting it run because we have too many programs running. We didn't really talk about this so much. I skipped the topic of what's called the long-term scheduler. But the long-term scheduler is his job to take things and and say, oh, we have too many programs running. Let's put some of these, let's freeze some of these and put them on the hard drive. So the point is, at a certain point, he may come back from the hard drive and we need to run him. That's what he's saying here. But either way, a program starts running. Either it's a new program or it's an old program that was frozen. It comes in. Without support, if we wouldn't do anything, we would put every program into address 000, we put them at the beginning. Inconvenient to have the first user process physically address always be 0. How could it not be? So further, addresses represented in different ways in different stages in the program's life. For example, in the source code, you write like the word counter, but the compiler, compiled code compiled code addresses bind to relocatable addresses. In other words, when I compile it, I don't leave it as 0. I leave it as 14 bytes from the beginning of this module. Because if I want to be on the 14th byte, it means if I want to say this, I assume we're at 0, but I don't say actual 0, I say 14 from 0. I don't say 14, go to 14. I say 14 from wherever you started. The linker or the loader will bind the relocatable address to an absolute address. That's what I was saying before. That the linker will change what I thought was 0 to 74,014. Because he'll put me in some other location. And then that previous diagram makes sense. So that's called address binding. And when is the address binding actually taking place? The loader or the linker. In order for the program to run, there must be a binding to a specific physical address. At the end of the day, I got to be somewhere. So there's different kinds of binding. What?
Address binding is when you make a specific location.
Is when I take the address that I wrote in my code and I put it into an actual physical location. Because remember, they can't all be, every program that you wrote in assembly, you wrote assuming you're at the beginning. But if I have 2 programs in assembly, I want to run them at the same time. They can't be both at the beginning of memory. So you need to bind them to some other location. That's address binding. You need to connect them. When will the physical address be decided on? So we just said in the previous slide that the loader could do it. Address binding of instructions and data to memory can happen at 3 different stages. Compile time. So that would be called absolute code. The compiler would just say, this is where you're going to be. I guess that's what you did in MIPS. You gave absolute numbers and that's what it was. It only works really if you have only one program. The code will incorporate the base register adjustment. In other words, that adjustment that we said that the base register is gonna be added to the code by the loader, won't be done here. Must recompile code if starting location changes. Right, now it's compiled into this code. If you ever want to put it somewhere else, you can't take, for example, you wouldn't be able to take a compiled code and give it to your friend and use his computer, because maybe he has different addresses. Or maybe somebody else is there. Load time, so it makes more sense to do it at load time. Compiler generates relocatable code, because the compiler doesn't do absolute code, it does relocatable code. Because the memory location is not known. The loader will create the absolute address. In both of the above cases, when the program actually is running, the addresses are actual physical memory addresses. In other words, they're set up. When it's running, all the addresses, that's where you are, and nothing's going to change. There's a third way of doing it, execution time. And that's really the way programs work nowadays. Execution binding time, binding delayed until runtime. Means even the loader does it, he puts it into a certain memory location, but it's not actually, well, we'll see, he's not. We'll see what he says here. What did I write here? The machine code does not contain a true physical address. Now the process can be moved during its execution from one memory segment to another. So what does it have? It has, let's say, it's still relocatable. The compiler generated relocatable, even the loader generated relocatable. It's just relative code. So so while it's running, we're gonna have to recalculate everything. Every memory request is going to be recalculated every time. Every time you do it. You say it's slow.
Yeah,
But what are we gonna do it? Who's gonna do it for us?
the hardware.
The hardware. And we're assuming the hardware is super fast. The machine code does not contain the true physical address. Now the process can be moved during its execution. Must compute the physical address on the fly. And when we're running. Must be fast. Needs special hardware support for address maps. And that's what we're going to use the base register and the limit register now for a different purpose. And that's what I was trying to explain. That's what I started off explaining before, because I was thinking ahead. Wait a second, where were we? Address binding.
Next slide.
Okay. The concept of a logical address space that is bound to a separate physical address space is central to proper memory management. So we've now kind of created a logical and physical address that are different. The logical address is what the CPU generates before the hardware changes it. Also referred to as the virtual address. Physical address, it's also referred to by virtual address, but I don't like to call it that. I like to call it the logical address. I just wrote that for years when on the exam is written by somebody else. It's not really called virtual address. Virtual address is we'll learn virtual memory. That's something else. Anyway, let's call it the logical address. The physical address is as seen by the memory unit. When you're actually, finally, you ask the memory to get me this piece of memory, that's what he sees is the physical address. In between, there's going to be somebody doing some translation, right? The CPU is going to create the logic, it just knows logical addresses. And there's somebody going to change it. Logical and physical addresses are the same in compile time and load time address binding. In other words, in both of those systems, by the end of the day, when the program is actually running, there is no such difference between logical and physical.
Yeah.
Because it was bound. It was address binding by the loader or by the compiler. Somebody bound it and now it's running and now it's bound. So there's no difference. Logical or virtual and physical addresses differ in execution time address binding only. So the logical address space is the set of all the logical addresses generated by a program, and a physical is all the physical ones. I mean, they don't have to actually be the same size. The address space. I mean, they should.
I guess some logical addresses will be accessed.
Yeah, it could be that I'll generate a logical, theoretically, I mean, they should probably be the same size, but theoretically, they could be different. It could be that two logical addresses will go to the same space, but right. Theoretically, you could have a hash function where the same two addresses will generate the same, but usually they're the same. Let's say they're the same. For example, as your program runs the code by, say, a load data command from location 100. In the runtime binding, this address will need to be converted to the physical address space. As you just said, load memory at 100. And that was left like that by the compiler and the loader. So now somebody's gonna have to change it to where it actually is. All this takes place while the program is running. Obviously, if this conversion is slow, your program will be slow. Hardware device, so there's something called the MMU, the memory management unit, which is going to do this for us. The hardware device that at runtime maps the virtual to the physical address, or the logical to the physical address. MMU may map via many different modes, methods covered in the rest of the chapter. So we'll see different ways of doing this. To start, consider the simple scheme where the value in the relocation register, now is what we saw before, the base register. We're now going to call it a relocation register. I see it says the base register now called relocation register. What we called the base register, which was just a place to check, has the compiled time binding or the load time binding given me an actual address that's within the range that it's supposed to be. That was what we were using it for before. Now we're going to call it the relocation register because we're going to use it to relocate our code. What do we mean by relocate? Move. We're going to take our code at 100 and add 10,000 to it. So now it'll be 10,000. So the register, that's the beginning point, will actually be added to our address. So consider the simple scheme where the value in the relocation register is added to every address generated by a user process at the time it is sent to memory. The base register is now called the relocation register. The value of the relocation register is added to every address when the user process sends an address memory unit. The program deals with logical addresses. It never sees the real physical addresses. Those are only, that's he just gives me a logical address and gets back to the result, gets back to value. Who's changing it to the actual physical? The MMU. Execution time binding occurs when reference is made to location in memory. As any time I actually do a load word or a store word, then I'll have to do some binding.
Yeah.
Logical address bound to physical address. Right. So here's a picture of what we were basically saying. We take the relocation register, which we put in 14,000, and the CPU runs the program with the way you wrote it in MIPS with the value 346. Let's say I want to go to address 346, and I want to get the value that's there. So he'll say, oh, but your base register, what we call the base register, is 14,000. So we'll just add it, and now we'll go to physical address 14,346, and then we'll give you back the result. So the MMU will be in the middle. Will be the middleman. Yeah.
Do we still have a limit register?
Yeah, we'll still have a limit register.
But it's accessed by the MMU.
It's like, yeah.
It's also in this picture. I mean, it's not. You'd have to add it to this picture. Well, once we got that address over here, we'll do some checks. What if I gave address a negative address? Then maybe we'd also check the base and the limit. We might. You say a negative address is silly, but it's not really, because when we do a branch,
Yeah, you got
we can branch up, and we can put a negative number in a branch. That's how you go up, right? So we do actually have negative numbers for addresses. Okay, so that's the basic scheme that we'll actually do. We'll use this MMU. We'll in between here, we'll do that other check that we did before, the base and the limit. Maybe we don't have. You could say maybe you don't really need the base, but you certainly need the limit. And that's our.
Shouldn't every negative number with adding a base be less than the base?
No, because we could have already gone forward.
I'm just saying if we add to
Oh.
the base.
Yeah, if we add it to the base, if the address is negative, then it would be, but if the guy tried, is what I'm saying, if the guy tried to say load negative 100, then he may have also said, he may have subtracted an amount from another amount that was bigger, whatever, he may have. We don't have to think about it, we don't have to think about that.
Oh,
But if, you're right, theoretically, I'm just saying, it's not written here. And this could go on anyway. You could say it's superfluous, depends. If the address could be negative, then it wouldn't be superfluous. All right, we'll stop here.
Or is it actually like a magnet?
Yeah.
It's pretty loud.